Thank you, Sarah. And good morning to everybody that's attending this part two of the 3D printing webinar. I hope everybody had a really nice Thanksgiving. I haven't heard anybody say they didn't yet, okay, or that they didn't have enough food. So I'm pretty sure you all would agree with that. But anyway, thank you for your time in attending this, and I really hope you find something useful that you can take to the bank after we're done here. But today, like I mentioned before, we're going to dig into some specifics of 3D printers, really, look at kind of what's out there, pros and cons, compare and contrast, okay? And start by looking at different types of 3D printing and then understanding parameters and specifications and what they mean for you and what you want to do in your laboratory. Compare and contrast popular printers, how to select the right printer for your workflow, and make sure that you know all the right questions to ask when you venture out and start looking at what's available out there. Okay, but first, excuse me, I kind of want to take a little review of part one and focus on a couple points that came back my way via some questions from some of you. With some of the things we covered in the first one. Okay, and so really, for me, this really is an amazing technology, and it has just offered us so many opportunities to not only increase business, but improve relationship with doctors, and just do all kinds of things that really were quite surprising to me once I dug into it, like we talked about before. From the ability to really cast well-fitting partial denture frames, I think primarily as a result of the resin that Whitmix has, their Vericast resin, which is extremely accurate, quite strong, and like I mentioned before, does allow the casting of frames without needing refractory models, which simplifies everything, and it brings, making partial frameworks and maybe partial dentures into the grasp of Crown and Bridge Labs if they wish to move in that direction, because this technology allows us to really minimize the equipment and the infrastructure we have to be able to do this. It's not quite as messy as it used to be back in the old days. We talked about custom trays and orthotics as either a service or possibly, a part of a newer and expanded business model availability. And of course, the idea that because of the nature of printing and the fact that, the frames are solid, there's no connectors to connect, and the accuracy of the margins is incredible, and the fineness of the margins. Amazing results are really right at your fingertips with both PFM frames and pressables and anything you want to process and investments. Now, we did talk a bit about mock-ups and diagnostics last week as well. And, I showed this particular case. And again, when you can provide the doctor with what I would call an orthotic or a mock-up or whatever you want to call it, so that a case presentation, the patient can see this instead of a model, it's just huge how much impact that has and how that results in, selling cases almost all the time. It's just terrific value-added service for the lab relative to the doc. And like I mentioned, I don't even charge for this because it's so easy to do. But I did get some questions back about how the digital diagnostics is done in 3Shape. And I don't want to spend much time on this because it's really not the point of this webinar. And we're thinking about maybe going into this deeper and into tissue management for implants and design and diagnostics on a later webinar. Again, some of your feedback on that would be really nice. If you have a topic you think would be of interest to you, share that with your friends at Whitmix, and we can see about putting something together. But really in 3Shape, I mean, this icon right here, which is for temporary unprepared model, is really the workflow for all the diagnostics. Surprisingly, I run into a lot of people that are not aware of this workflow. Okay, and the menu is slightly different after 2014, 2015, 16, 17, but it's basically the same workflow. It's on the same icon up there. And again, whenever you do it, you always want to make it a bridge. People forget this because if you don't, you'll have single units that just fall apart, okay, especially if your diagnostics includes Orthotics. So always make it a bridge with no connector because, again, you don't need connectors because these are all full contour, obviously. So anyway, the process is simply, you know, putting your library tooth in place, arrange it however you want for this particular case, and you just lay your, you know, sometimes you might have to prep a case if it's not additive. Quite often it's additive, but whatever is showing is what's left behind after you cut the tissue. Whatever is inside the model disappears, you know, like this. Or if it's laying on a tooth, it'll become a veneer. This is also a great workflow for doing like Maryland Bridge wings, okay, where you really don't have a margin defined. And the beauty of this is that you don't have to define a margin. When you tell it to cut to the gingiva, and here it says 0.13. I usually cut at 0.1, 0.15, just enough so it'll seat on nicely, okay, back on your model. Then you cut it. Okay, and everything, like I said, that's inside the model just disappears, basically cut the tissue, leaving you your STL of your diagnostics. And from there, if I'm making a diagnostic model, let's say a wax up, I'll actually Elmer's glue this to the model and then make my duplicate. If I'm going to be using this as a mock-up, if that was appropriate, then I would be printing it. So you can do a number of different things with this. But again, if you're going to mill it in wax, in white wax, you can just, with Elmer's glue it right to your study model. And one other quick tip I'll give, that if the diagnostic case requires prepping of the teeth, then what I do is I scan the model first as a pre-prep, stop, go do my preparations, then come back and scan that as a working model so that I can fade in my pre-op so I can kind of see where the teeth were before I prepped them. And that's really quite helpful. So anyway, enough of that. And again, if you want to dig into this deeper, we can, you know, on how to specifically reuse this diagnostics and other things associated with that. But right now, let's just take a look at different types of 3D printing that are available on the market. The first one I want to talk about is called extrusion. And this is a real interesting technology. It basically just uses a wire of plastic that goes through, it's fed down to a heating element, which liquefies it, and then it squirts out of a nozzle and is deposited. It's basically a hobby printer. And these things, you can find them on Amazon for like $150. They're really kind of cool. They don't have very much accuracy, but for kids and for just goofing around and doing things, they're really kind of amazing, and they're really inexpensive. And you can change colors in the middle. You just pull out one rod, put it in another. You know, they're fun, but they're not really practical for what we do. But they make a great Christmas present for younger kids. Jet printing, now this technology can actually print more than one material at a time. And this one is where people are kind of looking potentially for doing, you know, 2 or more colors like dentures, you know, pink and white, or pink and multiple shades, and maybe even layering of the actual teeth with this technology. But it's really difficult to change materials. It's the post-processing is far more difficult because you can have multiple materials. It's very slow and it's very expensive right now. But this is one to keep our eye on, which may be the modality that will end up being used when we finally get to actually printing complete dentures or complete restorations that are actually layered. It's very interesting technology, but for today, it's not practical for our business. Now, granular powder, okay, this is quite similar, but it's really mixing powders with binders, okay? You can infuse different colors. So it's one powder, but the colors can come from dyes, so it's a little more sophisticated and allows us to do 3D printing with a variety of colors based on the kind of dyes that the system can deliver. Again, it's used a lot for prototyping of products that companies are wanting to bring to the market. Not really so much for dental. The resolution is too low. Again, the post-processing is difficult, and it's quite expensive. But again, between this and jet printing, I think we're going to see a little more interest in these areas as the years go by and the technologies get developed and the price comes down a little bit. Now, most of us are familiar with this SLS, selective laser sintering, also called SLM sometimes, selective laser melting. And this is the process by which metal is laser sintered into copings or partial frameworks. You know, I know Bago was doing a lot of that for a while. Argon is doing this now. A lot of people are having their non-precious copings produced this way from their digital designs because, you know, casting some of the non-precious alloys is not the easiest thing in the world. And the accuracy is good, the resolution is good, and, you know, you can print things other than metal, plastic, glass, partial frames, all kinds of things. So it's a really good technology with a lot of dental applications, but the units are in the range of $1 million. Okay, so really not something that we can look at for our labs, but we can utilize it in an outsource basis with providers again like Argon and others today. Now, when we look at our world, really the light polymerization type of 3D printing is really where we are pretty much 100% today in laboratories. And all the machines we're going to look at and talk about and discuss are in this class of 3D printers. And within that, there's two distinctly different methods of achieving 3D objects through light polymerization. One is called SLA, which stands for stereolithography, and the other is DLP, digital light processing. And they are really quite different in what they do, what they bring, what they cost, and what you can do with them. And so understanding the difference is really quite important. And so if we look at SLA, basically it means that a laser is being directed down to the build plate and is polymerizing one layer of resin at a time. And this was really the original technology developed for light polymerization of resins, was the SLA using the laser. It's actually an older technology. It has, interestingly, lower resolution than DLP, which when I first started looking into this actually surprised me, that the best unit on the market today is about 140 microns. And we'll talk more about that later on and what the implications of that are, okay? It's quite a bit slower because the laser has to trace the outline of the object on each layer, like line by line by line. And so it takes it actually quite a while to do each layer because it's traced or drawn or you might even call scribbled by the laser, each layer before the build plate moves down to allow for the next layer to be built. Okay, but it's also quite a bit less expensive than DLP. Actually much less expensive as it says. Now, DLP is the newest technology for achieving light polymerized 3D printing. And it uses a DLP projector, a light source bouncing off a DLP chip, a digital light processing chip, which if you don't understand this technology, it's miraculous, okay? Basically, really, it's millions of little tiny mirrors that flip off or on, so it reflects the light up to the object based on what you want to print. The mirrors are either on or off, and it makes the image that way. So the resolution depends on the size of the mirrors. So when you have a really high resolution or a fine resolution like 75 microns, that's almost the size of the mirrors. So again, it's a miraculous technology, but it works extremely well. And it's very fast because each layer is exposed as an image, as a picture in one piece. Boom, it's exposed and it moves on to the next one. So it's many, many times faster than SLA, which makes it great for production, obviously, and for the lab. It is, though, considerably more expensive. And we're going to talk more about the pros and cons of these types of technologies because they both have places in the laboratory. But again, which one is right for you depends on what you want to do. And hopefully by the time we're done, excuse me, you'll understand more about that. Now, the resolution of printers, we talk a lot about resolution. We talk about resolution in the many arenas, and it's a very important concept for printing as well. But there are two distinctly different types of resolution. There's what we call Z resolution, which is vertical. The Z axis is the vertical axis, so the taller the object, the longer the Z or vertical axis is for that object. And then we have XY, which is horizontal, two-dimensional horizontal, which really is the images that comprise each layer. As we build the layer, the Z would be a measure of the thickness of each layer. So if we put a little graphic up, okay, let's say we're building this dome. If we build it in 100 micron layers, you can see what will happen is that there's bigger stair steps between each layer, which means that the surface smoothness is not as good. As we increase the resolution, which is by decreasing the microns, okay, which sometimes confuses people, higher resolution is a smaller layer, we get actually smoother edges, but many, many more layers. And so since each layer takes about the same amount of time to cure, at least in a DLP type of system, then this would obviously take longer, but give you a better result. So, you know, deciding how you're going to utilize this in your lab is another thing that we will talk a little bit about. And one of the things that can help you speed up a print, you know, or not, depending on how fine you need the resolution or the edge or the surface to be, how smooth. Okay, now, one thing to keep in mind is that the vertical is mechanical, it is not digital. And what I mean by that is there's a mechanical transport that moves the build plate a little bit up between each layer. And depending on what kind of resolution you have, that means that that plate has to move just 50 microns before the next layer is exposed and polymerized, and then 50 microns, then 50 microns. And so, you know, some of the printers, the transport for moving that build plate is not as accurate. And you don't get really as consistent a layers as sometimes you would hope for. And that's something to that's a good question to ask about the accuracy or the dependability of the transport. Okay, some use chains and belts, some use screws or augers. There's different ways for transporting the build plate up and down, but that is what determines the Z axis. Okay, so it's an important consideration. Okay, so we talked about this high resolution being smoother surface, but takes a lot longer. Now this will show you what 50 microns looks like. And because the top of this coping was almost flat, in order to produce it, there's a lot of layers here. You can see them, and each one of these little lines represents a 50 micron layer. So as you decrease resolution or go to thicker and thicker layers, these stair steps become bigger. So, you know, in a case like this, we want like as close to the finest resolution we can get to try to eliminate this. And I will say this, that early on when we did some castings, you will see this in the castings. And we had to have some conversations with some dentists about the fact that this wasn't bad, this was the nature of it. And in fact, hey, if you really want to get to it, maybe it helps increase cement retention. Now, you won't see them so much on axial walls, okay, but you'll see them on almost flat surface because the layers overlap, because the system is trying to get a flat surface out of layers. And again, at 50 microns, you don't really see it on the certain. In fact, this model was done at 100 microns, and you can kind of see the striations, but they don't really affect the utility of the model. So there's an implication here that we can use higher or lower Z resolution or higher numbers, higher microns, when we're printing certain things. And I'll talk a little more about that, okay? And again, if we increase the thickness of the layer by decreasing the resolution, it'll print faster too. So that's really something important to consider when we're looking at printers. Okay, it's not just a resolution, but is it adjustable? So the most important aspect, though, is the XY resolution, or the actual pixel size or resolution of the image that gets printed for each layer of the object. So you can see that at 140 microns, there's quite a bit of stair step around the edges, okay? And at 75 microns, it's a whole lot smoother. And, you know, this is actually the digital portion of the function of the printer. In other words, this is either digitally projected in a DLP, or it's digitally scribed by a laser in SLA type of printing. So what this does, though, is determine the thinness limit that you can print, basically for margins and edges. So obviously, if you're doing any kind of crown and bridge for frameworks or pressings, then you definitely want the highest resolution that you can get in order to have the finest edges of your margins. At 140 microns, which is 0.14 millimeters, probably the thinnest margin offset you can produce would be close to 0.2. You can't quite get that far, okay? And there's always a little bit of splatter. The laser actually splatters out and polymerizes a little bit more resin on the edges than it's just the nature of it. Same thing happens in DLP, but not quite as much. Again, 0.2. Okay, that's going to leave some finishing, 0.7, 0.8. That's a much finer margin offset, and it gives you an actual finer margin. It requires less finishing. So important considerations when we're doing this. So in SLA, this represents the diameter of the laser. So you can print to, well, theoretically 0.14, but again, not quite. And so that's good for trays, splints, guides, and like ortho models, not models with removable dies. The accuracy is not there for that, and it's not there for crown and bridge nearly as much as with DLP, where the pixel size ranges from actually less than this, 37 microns to 75. So for crown and bridge, RPDs, models with removable dies, and ortho models, temps, guides, etc. Something with this kind of resolution can address everything. Again, though, there is a big cost difference as well. So this is a worthy question to ask. Now, this arena, talking about wavelength, and that's the wavelength of the light that's in the machine that's actually curing or polymerizing the resins. And there's two basic categories for this that are available today. There's 385 nanometers versus 405 nanometers. Now, to us, 385 is actually UVA. It's actually in the UV range. Our eyes can't see it, okay? And 405 is actually just barely in the visible light range. It's sort of a blue-purple light. So this would be considered visible light curing. This is ultraviolet light curing. And there's some distinct differences, okay? One of the maybe biggest is the ability to print clear materials. A 385 nanometer light source or a 385 or a UV 3D printer will be able to print clear materials. This may or may not be important to you, but that would include things like trays, surgical guides, those kind of things. 405, at least right now today, cannot print clear materials. They'll either be slightly tinted, like a blue or a pink or an orange color, and they tend to discolor a little bit or become cloudy if they're, like, let's say, put into an autoclave and heated or just sitting around over time. Is this important? I don't know, but it's something to be aware of for what you're going to be using your printer for. Okay, the 385 actually is a more energetic wavelength of light. There's more energy in it. It actually can cure a layer a little faster than a 405 nanometer. This isn't a big deal, okay, at all. It's really, I don't know, you wouldn't see a big difference, but it is a little more energetic and it does cure resins a little faster. This is a newer technology versus an older technology of 405. A lot of the first printers were in this wavelength. Now, from what I see, there's a little bit more resin development going on out there in 385 resins than in 405 resins. So perhaps this might be a better choice based on what comes down the pike in the future for more and different types of resins for applications in our industry. And again, quite a big difference here in cost. The UV light sources are just more expensive than the visible light sources in these printers. Now let's take a look at a couple different printers that are popular on the market and just see what they bring to the table and kind of what some of their pros and cons are based on this information and based on how they function. The Asiga printers are DLP. The Asiga Pro has a decent sized build plate, 5.6 by 3.1 inches, which and it can do everything. We've already talked about crown and bridge, frames, models, with or without removable dies, tray splits, clear guides, all this stuff. And the build plate can hold about this. You could put 2 full arches on there laying flat. And that's important to understand, that if you can lay them flat, they're going to print a whole lot faster because there's less vertical. The amount of stuff you put on a build plate does not affect the build time. It's how tall it is. It's how many layers it's going to take vertically to build this object, because each layer is exposed in a DLP printer, boom, as one image, and then it moves to the next layer. So it's really time is based on thickness. In SLA, that is not true, because the laser has to trace around every single object that's on the plate for that layer. So the more things there are, the longer it can take. Just be aware of that, if time's important. And you can lay things on their side and build them higher. Of course, here we can put more models in, but they stick up vertically and it's going to take longer to print. The Form 2, which is a very popular printer out there, okay, is an SLA. The build size is huge, 5.6 by 5.6. But look at this, the resolution is 140 and it's a 405 nanometer, not a 385. And that brings certain things, certain considerations to think about. Okay, well, number one, being such a huge build plate, we can put, 2 sets of full arch models on there at one time. That might be huge for you, okay? You can put a lot of vertically set models on this. Again, huge build plate, but because the resolution is 140 microns, 0.14 millimeters, you're not going to be happy with it if you're wanting to do crown and bridge, parcel frames, or models with removable dies. Now, ortho models or study models, no problem, okay? In fact, higher resolution is kind of good for that, but not for these things. And then the fact that it's 405 means you can't do clear surgical guides with it, okay? They'll have to be tinted, like I said, and they will also quite often discolor a little bit, although there is some work being done in that arena. Now, the EnvisionTEC printer, which I think everybody's familiar with, is also DLP, okay? The build plate is almost the same size as the Asiga Pro, very, very close, but it has a resolution of 140 and it's 405 nanometers. So I think you already know what that means, okay, as far as this goes. It's going to build about the same amount of stuff as the Asiga Pro. Again, it's almost identical size build plate, but because of the resolution, you're not going to want to do these kinds of things with crown and bridge and frames and removable dies. And you're not going to be able to pull off clear surgical guides. Again, may or may not be a problem for you, okay? And the Bago printer, again, it's DLP. It's got a nice resolution, 60 microns. It's a 405 nanometer. So I'm sure you can answer the question as to what it's going to be able to produce, okay, well. But this is one little problem. This build plate is not quite big enough to put 2 full arch models on. So that can be a little problematic, and I'll show you in a second kind of what that means. And you can't build this many models at all on this build plate. It's unfortunate that the area is a little bit small on this printer for what we do. But the 405, but back to this resolution though, 60 microns will give you really stellar crown and bridge and margins and removable dies. But quite often, in order to print a full arch model in the Bago, we have to do them like this, angle them upward to fit them above the build plate. And now you're really increasing the Z-axis, and a build like this will take many hours to do, as opposed to maybe about an hour and 10 minutes if it's laying flat. So probably more like 4 or 5 hours to do this. Again, though, the 405 eliminates clear surgical guides. So this is the kind of stuff that's really important for you to be thinking about when you're looking at printers and kind of weighing their abilities versus their cost. Now, open versus closed is, I think, really kind of important. Open meaning that you can utilize third-party resins. In a lot of printers, you are required to use resins produced by the manufacturer of that machine, because printing a resin is not just printing a resin. There's a lot of stuff that has to be considered when you're doing this in terms of how to expose the layers properly and how much time the light needs to be on. It's really a very complex situation. So the open printers on the market currently today are the Asiga, Formlabs, and one called the Rapid Shape. Although I will say the Formlabs, while in its structure is open, you really don't have access to exposure times, exposure intensities for each layer like you do in this printer. And the Rapid Shape is very similar, so it's kind of a closed open system. It's not really user friendly. It's not really available to the end user to really change the kinds of things we need to change to be able to make a given resin print well. And I'll talk a little more about that in a minute. Now the Varseo, the EnvisionTech, and there's one called a DWS, which is a competitor in this arena. They are totally closed, meaning that you are forced to use the resin sold by the manufacturer, and I guarantee you that you will pay a lot more money for those. Okay, so what I want to do now is just kind of dig down and really look directly at the Asiga printers. And you know, when I was first doing my research, and I really didn't know where I wanted to go, and then I discovered these printers. I got to tell you, they kind of blow my mind. For many reasons, which we'll go over here. You know, number one, productivity. You can print a lot of stuff on that big Asiga Pro. Okay, I mean, a lot of models you can vertically stack things. It's crazy how much you can do in one of these printers if you're a high production laboratory. Time-wise, as far as doing this kind of stuff, hour and 40 minutes to do flat models, maybe 3 hours, 10 minutes to do vertical. And something like this would be pretty much an overnight to be able to do something like this. So give you an idea of, again, time is all about the z-axis and the vertical. And if you don't have an extremely accurate z-axis transport, a mechanical transport in your printer, you're not going to be able to do this well, okay? You'll have a lot of discrepancies and inaccuracies in the various layers of this. So if that's your plan to get into high production, it's really worthwhile looking at a printer like this one, like this Asiga Pro. Cost-wise, it's actually kind of remarkable. Models, quadrants, $2 to $3, full arch $5 to $6. Ortho models, if they're kind of thick, which they always are, that's a lot more material, about $9 to print that. Copings and crowns are ridiculously cheap, okay, to print as far as, this is all material costs, okay? This does not figure in the cost of the equipment, okay? That you'll have to kind of prorate that out yourself if you really want to really figure the ROI on this investment. Surgical guides, about $4 in material, partial frames, $1.25, custom trays, $3. So this will give you some idea of, you know, once you jump into this, what it's going to cost you to produce these things just in materials. And I will say this, that materials, they are not all created equally. And I've tested a lot of different materials out there, and some perform well, some not so well. The materials from the Witmix cells are priced quite well, about half of what you'll pay in a closed system with a closed system printer. And they've been vetted extremely well, and they really perform quite well. You know, the model materials, there's a new one now I didn't put, sorry, it's a little bit more of an ivory color. It's not so much as orange color. It's a little better for, let's say, all ceramics. They do have the ivory model material now, and I apologize for not showing it, but it's not quite this white, but it's closer than this. The guide material is a perfectly clear, and the tray material. So one question I had was, well, if I've got model material, why do I need tray material? And vice versa. Okay, why can't I print my trays with model material, or vice versa? And the reason why is because these are meant to go in the mouth, and so they don't have any BPA's in them. They're FDA approved for that kind of stuff, whereas these resins are not, and they have other additives to make them more applicable to models, which aren't necessarily as healthy in the mouth as this would be. So it's worth, you know, looking into what's in these resins as well, and how they're produced before you just go out and buy them. All right. Again, though, the cost of this within the dental industry is actually quite competitive. It's quite nice. And of course, you know, for me, because we have 4 different materials, the changing of materials is really, really easy in the Asiga. The tray is just a plastic tray. You can see it here. It's mounted. There's these little grips. You just pull these up with your fingertips, and you lay these arms out, and the tray just comes out. Put a lid on it, put it in a dark cabinet, and put the other tray in. So you want to buy 1 tray per material, but once you do that, it's about 30 seconds to switch out to a new material. And since it's all in the tray, there's nothing to clean when changing one material for another. Just swap the trays, which is very convenient. So when we're looking at the lineup of the Asiga printers, there's basically the original lineup was these 3. And then we're going to talk about something else here a little bit that's new on the horizon. The Pico 2, the Pico 2 HD, and the Pro 2. Okay, and these sizes are about relatively accurate, okay? And the Pro 2 is a big machine. It's almost 3 feet tall. Okay, so it has a pretty big footprint, worth keeping in mind. Now, these all have a variable Z-axis. Now, why is that important? And it's easy to set. It's just a touch screen on the front. You just set it. Because for things like, and not this is a removable die, but for ortho models, guides, orthotics, trays, those kinds of things, you can increase this resolution a lot to, let's say, 100 microns or more, because we don't need those fine edges. These will print much faster, and they're perfectly good. So if I'm printing this stuff, that's what I love about these printers. I can just dial up the Z resolution to 100, and boom, print these twice as fast from a 50 or 60 micron and have a perfectly acceptable result. So being able to do that, I think, is really, really important. Wavelengths, 385 or 405, your choice. I know for me which one I would go for. For you, that may be different. The interface is either Wi-Fi or with cable, without cable, between your computer and the printer, which is really cool. There is a Wi-Fi interface, so it can be wireless. It accepts 3 different types of files. STL is what we use. I'll be honest, I don't even know what SLC or STM are, but if you run across one, you can print it in one of these printers. I should find out more about that. Now, these 3 also come in a UV version, which means it's a 385 nanometer light source. And we already know the implications of that, right? Printing clear materials, number 1, slightly faster, more energetic, okay? And really that's the key difference. But remember, the UV versions are slightly more expensive, okay? So again, breaking it down a little further, this Pico 2 is available in 2 machines. One's a 50 micron resolution, 39 micron resolutions. These are high resolution, very detailed printing machines. The build plate is 64 by 40. The 75 means vertically how high you can go. The last number in all these examples is how high you can go vertically. Okay, and this will show you about what you can fit on that build plate. Okay, notice full models won't fit. A little partial frame would have to be vertical. You can put tiny little models on here. That's the limitation of this, but super fine detail. Probably much better for crown and bridge. You can get this in the 39 micron resolution, which is even finer, but as you can see, it offers even less space to build, because as you increase resolution, you decrease the image size, okay? So, or increase the image size. So you really can only, you will be able to fit less on a higher resolution machine, and that's typically true in any given printer. The higher the resolution, the less stuff you can, the less area that you have to print on. Okay, it's like moving the projector closer to the screen. Basically, the image gets smaller. So the Pico 2 HD is a 37 micron resolution machine, which is actually better than the best resolution on the Pico 2, hence the HD. And if you'll notice, though, it actually has a slightly bigger build area than the 50 micron version of the Pico 2. So if you're interested, if all you do is crown and bridge, and you're really interested in the best reproduction of your designs, this might be a good one to look at. Very high resolution, super fine margins, 0.3 0.03 millimeters for your margin offsets. Super fine. Again, won't do full models though, and you could be caught having something you don't like if you were wanting to print models. Now the Pro 2 is really the big production workhorse. Big build plate, also 200 millimeter vertical, so you can stack it. Okay, it'll hold a lot of stuff. Okay, a lot of models vertically, four double sets of models, uppers and lowers. And the machine itself can be reconfigured to be, it's a 75 micron native. It can be set to 62 or 50 microns simply by moving the projector inside the unit closer to the build plate, which of course makes the build area smaller. So at 62 micron, you lose some build area. And at 50 microns, you lose a little more, okay? But you increase the fineness of your edges. So this machine does give the laboratory the opportunity to physically move the projector, which is easy, and increase the resolution should you ever want to, at the sacrifice of the build area on the plate. Okay, so, and to give you an idea about relative cost, and this varies, these are just numbers that I throw up, and I really don't want to stay on that because, hey, there's always deals to be had, and yeah, that's, if you're looking at one of those, you talk to the Whitmix salespeople. But all the Asigas come with what's called Composer software. It's very graphical. It's very easy to use. It's free, free upgrades. No dongles, none of that. Okay, and it also has Apple and Windows compatibility. If you're a Mac, it's kind of nice. It's the only digital nesting software that I know of that's actually Mac compatible that's out there. If you're a Mac, now I saved this for last. The Macs. This is the new kid on the block. This is basically a new product out of Asiga, specifically for dental. The build envelope is 119 by 67 by 75 high, so it doesn't have the vertical height. You can still stack, but not as much as the Pro. And it fits, and these are the three sizes of the Pro. It's basically the middle size build plate that you could achieve with the big Pro. So it's the same engine in size, but the size is really small. It's toaster oven size, a little taller. So the footprint is really, really nice in most laboratories as opposed to the big Pro. It's a 62 micron resolution XY, which is great for crown and bridge for anything you want to do. Okay, and you can see in my lab, you know, we had the big Bago here. It's big boy way back when. Okay, took up a lot of space, and this is now the Max, and this is the same base that we have it sitting on. You can see the difference in the footprint size of this printer versus the Bago printer. And the Pro 75, the big Pro printer, is about the same size as that Bago printer. It would take up this whole space here and go 3 feet high. So in my opinion, this thing is fantastic for the average lab. Again, it's all those Asiga printers are touchscreen, menu driven, easy to do. They also, you have this exact same menu on your computer through the Wi-Fi. So you can control it from your computer, you can push it on the front screen, you can control these in a number of different ways, really easy. The graphics are great. The native colors it comes with are really easy to differentiate your STL from your pinning and from your pens. Really, really easy to use. The build plate on the Macs allows you to do quite a bit. I mean, you can put a lot of stuff on that build plate. If you're so inclined. Vertically, you can go 75 millimeters vertically, so you can do some tiering and some stacking if you have high production demands. Again, not quite like the Pro 75, which is 200 microns, but still, you can get three levels if you need to. The Pro will do this. The Max will do probably 2 of these levels to here. It would give you this amount of productivity if you needed it. This particular screen, this is really, really, really important stuff, okay? I don't know any other printer that has this capability built in. All these things, but mainly to me, single point calibration. You can calibrate any of these printers in under 30 seconds, which is remarkable, okay? You can focus the LEDs. You can do anything you want with these printers. It's totally open architecture. Again, Internal radiometer. That means it has its own built-in light meter, so it's constantly monitoring the amount of energy coming from your light source. This is extremely important because that thing is working while you're printing. And so if you have a little voltage drop that you don't even notice, it means the intensity of the light that's exposing your resin goes down just a little. Well, it detects that. And it will actually, on its own, increase the exposure time a little bit to always deliver the same amount of energy, which is intensity of light times time to get the amount of energy that's needed for each layer. If your voltage is down a touch in your lab, it'll go a few microseconds longer in the exposure. If it's up a little bit and there's a little more energy coming out of your light, it does vary. It'll cut the exposure a little bit. So every single layer is always exposed exactly like it needs to be. And I didn't realize how big a deal this was when I first got into this technology, but exposing the resins exactly right is the key to getting consistent, super accurate, perfect results with the right hardness and no edge splatter, which basically sort of fuzzes the edges of you build a little bit. Really, really important. Nobody else is doing this. It also lets you calibrate your light source anytime you want really easily. And the open material system. This is crazy cool, okay? And is probably the one thing that would get me to buy this, because when we talked about the mock-ups and diagnostics, right? Somebody asked that white resin, and I show this a little bit hesitantly because these fun to do resins, that's where it comes from. It's the snow white, and they also have colorants you can drop in, yellows and browns, to tint it like you want. But be aware, these resins are not, FDA approved for intraoral, all right? And, the implications of some of these third-party resins, you really need to do your research about what's in them and are they okay to use if your plan is to do things intraorally with them. However, any resin that's out there, like I said, the exposure of the layers is absolutely critical. So the Asiga lets you put any resin you want on a glass slide, okay? It's got a special function that lets you expose each dot for a preset amount of time. So with this one, you do 10 dots, 2 slides worth. The first one you expose 1 second, the second one 2 seconds, 3 seconds, 4 seconds, all the way up to 10. And what you do is you take those dots and you measure them and see how thick it cured in that amount of time. And you plug that information in to some calculations, and that again goes into a material file, which tells the computer inside the printer exactly how to expose any resin properly. Now, it takes a little bit of time to do this, but the end result is you can create a custom material file for any resin that you want to print that you run across out there, probably in about 30 minutes. Okay, you can do it. All right, so you just need really good calipers to 3 decimal points and some glass slides, and boom, you're done. The functionality is built into the printer. So, looking at this technology, it's really kind of crazy, okay, what's going on out there in the real world with 3D printing. And a lot of the stuff you hear about. There's some new materials always on the horizon, titanium, zirconia combinations that can be printed for printing the final high-strength restorations that don't require sintering or require post-processing. Crazy cool, okay? And the ability to build colors into this as well. Okay, full contoured high-strength ceramics. Again, printing final restorations, including coloring and shading with other ceramic materials. Antimicrobial plastics that kill bacteria. Looking at these kinds of things, perhaps for temporaries and long-term temporaries in the mouth. And the bioprinting, which you're hearing about, where you can actually print human cells. They're printing ears, they're printing noses, they're printing all kinds of human tissue for transplant and for burn victims and cancer surgical victims, different things. And, it's amazing, almost scary what this kind of technology brings to the table. It really is an incredibly exciting technology. So that brings us to the end. We've almost covered the hour, a couple minutes left. I really want to thank you all for your time. and your attention. I hope some of this clarified some of your questions and gave you some food for thought and help you become a little more comfortable with this technology if indeed you are looking at jumping into it here in the near future. So with that, I'll sign off, hand it back off to Sarah, and wish you a good day. Thank you.
All right. I will leave it open for maybe 1 more minute for questions. I don't have anything that came in right now. But if you do think of something offline, you can, there is a place where you can write in your comments with the CE test that I will give you for credit. You can do that, or you can always email us at webinar@whitmix.com anytime you have any questions, and we'll get those questions to the appropriate people to get back with you.
Yeah, and I'd like to encourage people to also maybe comment on other topics they might like to suggest for webinars, or maybe some portions of this to dive deeper into, like I mentioned before, maybe diagnostics or customized controlled tissue contouring, utilizing diagnostics for implants, a variety of different things that we could cover if people have an interest. Just let us know.
Well, I think for now we're going to go ahead and end the webinar. Again, we will be sending out an email with a link to the recorded webinar and CE information either later today or tomorrow. One question did come in. What type of support is available from Whitmix?
Oh, that's a really, really good question, because I need to put that in there, because one of the key things, no matter what you're buying, whether it's a CAD/CAM system, a mill, a printer, you name it, you really want to research your supplier or your vendor and maybe even talk to labs that have worked with them to see if they, number one, have decent support people and if they're available. And the answer to both of those with Whitmix is a resounding yes. And in fact, their support staff is growing a lot these days. They've brought on some new people that are extremely competent, and they are really good. They know this equipment inside and out, and they're available pretty quick. Not always at the very moment you need them, but within a short period of time, they will be there. And I have had zero issues getting past any technical problems that I've had with their support staff. And and I would always recommend that if you're looking at buying something from a particular company, have them give you the names and phone numbers of a couple labs that have bought from them, and give them a call and ask. And I would be very surprised if you didn't get, like, boom, 5 stars, thumbs up in terms of support from anybody that's working with Whitmix. They really are good at this.
Another question that came in is a backup available?
What's a backup? Oh, you mean like if your printer goes down? A loaner? I assume that's what they mean. And that is a really good question. I'll be honest with you, I've never had to utilize that service. What I will say is that from other experiences I've had with Whitmix, when my scanner went down, I had a loaner the next day, okay? When I had some issues with my mills, I had what I needed to fix it the next day. And I've never known them to leave anybody hanging. And so they also, Whitmix does also do outsourced print services. So in the event that your printer went down, they will step right up and handle any of your printing needs for you in the interim of getting it fixed. As far as whether a loaner would be sent, I don't know, but that's a good question. I will find out.
Okay, another question that came in is, can people come to visit Whitmix to see the Asiga printers?
Oh, yeah. Absolutely. One thing you may want to keep in mind is that, every fall they do a 2-day digital symposium there, which of course includes a tour of the facility. And every year it's kind of a different topic. I think we've done it now 6 or 7 years in a row. But if you live near Whitmix or you're ever in Louisville, you need to call them and pop in and get a tour and go see all this. They love to do that, and it's quite impressive, actually. So yes, definitely.
All right, I think those are all the questions. So I just want to thank everybody for attending, and be on the lookout for that email, because we will be sending it out here shortly. So everybody have a great afternoon. Thank you.
Thank you.